Hi, everyone. I'm Sabrina Hong, pronouns are she, her, and yeah, I graduated from UCLA some time ago. I'm not going to say the year. Did my bachelor's in astrophysics while I was there and doing some undergrad research with Professor Renee Ong in the astronomy department. Really, really happy to be here and excited to talk about quantum.
Okay, so while we have Daniel joining us on the side, maybe I can start sharing screen and we can start presenting. So Daniel is going to present on the second half of our presentation, so maybe we can get started and he can join us then. How does that sound?
Cool.
Sounds good.
And Abe and Sabrina, can we pause you to ask questions during the call? Okay.
Yes.
Awesome. Feel free, everyone. They're among the subset of my favorite people, so I'm super excited for this presentation. Go for it. And you're muted, Abe. I'm not sure if that's on purpose. Oh, and Daniel is here.
Yeah, I'm here. Finally.
Abe, you're muted. Okay.
Can you still hear me or still muted?
We can hear you, Abe.
now.
You're good. Okay, awesome. Thanks, Daniel, for joining us. I'm not sure if you heard when I said this. And then are you able to see our slides?
Yes.
All
yes.
Good. Okay, perfect. All right, so let's get going. So today we're going to be talking about superconducting qubits, and the group here is all from Google Quantum AI, and maybe just in the interest of saving time, I'll start very quickly on these slides. So the outline of this conversation is going to be like we have here, where we'll first go through an overview of the infrastructure used to drive quantum computing with superconducting qubits, just broadly speaking. We'll quickly talk about how we engineer qubits from superconductors, and then go deep into two topics. One on gates and device characterization. That is where my colleague Sabrina Hong will take over. And then the second one on the readout problem, and that is where my colleague Daniel Sang will take over. And then we're going to make sure we leave some time in the end for questions and also for you to ask us about any questions that you might have, whether about the topic itself today or work in industry and careers and things like this. So as I mentioned, the three of us here are all joining you from Google Quantum AI, and maybe just to give you a brief picture of what facilities we're working with, I have a tab here that I wanted to share with you. So hopefully you can see a tab that says Discover the Quantum AI Campus. Is that right?
No, it's still showing the slides.
No.
Gotcha. Okay, give me 1 second to switch over.
Yes.
Okay, very good. So very quickly, I just want to start by telling you a little bit about what the infrastructure is that we're working with. So all of us are based in Santa Barbara, California. And our goal here, as always, is to try to build these quantum computers and do it in a scalable way and try to use them to solve problems. So as you walk into a typical lab that does work with superconducting qubits, the infrastructure that you see is something that looks like this. So just broadly speaking, if you just walk into the lab, you'll see some structures that repeat. So for example, you see these two sections over here that have the fridges themselves. And then you see the supporting electronics and associated tools next to each of these quantum computers. And now the question becomes, what is inside each of these systems? So as I mentioned today, we're talking about superconducting qubits. Each of these systems is actually a fridge that cools down our systems to about 10 millikelvin. And if you uncover it, what you'll find is that it's a system that has several wires going up and down, a system that is cooled down to 10 millikelvin at this stage, and everything above it has a higher and higher temperature. So the goal is gradually you cool down until at this very bottom stage, you can anchor your sample and your device. And that's where your quantum computer lives, at about 10 millikelvin. Everything that you see here is with the intent of controlling and driving that quantum computer. So for example, you see a number of control electronics over here, and we'll talk a little bit about that in Sabrina's section. But you also see a number of wires here, and they have multiple purposes. Some of them are reading out signals from the quantum computer itself, and Daniel will tell you a little bit about that. And some of them are making sure that our qubits are wired up appropriately so that we can control them. So within the very bottom of that fridge that I showed you is our actual quantum chip that does the computation. And the way we connect to the outside world from that quantum chip is by using infrastructure that looks like this. So for scale, you can see the hands of one of our researchers here, but these many pins are used to connect to the many connecting pads on the chip itself. And so this overall packaging is putting together the quantum chip in a way that it can be mounted to the base of that fridge. If you look inside that packaging, what you'll see is the actual chip. So this is what it looks like. You should see a grid of qubits and a grid of readout wires also that are used to control the qubits. Fundamentally, this is aluminum. Aluminum is the superconductor that we're using in this work, and it's deposited on top of silicon material. So what you're looking at here is aluminum patterned on top of silicon. And as I mentioned, there are multiple components to the system. There is the question of how you make the qubits themselves, and then also how you connect the qubits to the outside world. So I'll get into this a little bit when we talk later, but the most important question I want to show you is this discussion of how the qubit itself is made up. So what you see here is the very elementary component of the system, and that is how we pattern our qubits. So what you should see here is very thin layers of oxide material between two layers of aluminum metal. And that oxide material between two layers of aluminum metal itself ends up becoming a superconductor, insulator, superconductor. And that becomes the basis for what we call a Josephson junction. And that Josephson junction will become relevant in our later conversation. So hopefully this gives you a picture of when you zoom into the fundamental pieces, the qubit itself looks like this. And we're talking about 10 micrometers of size here. But when you zoom out, the components that are required to sort of wire to the system and control this quantum computer reach out to a scale that you see at the size of a room. So let's start talking about what we actually need to make these qubits. So let me go back to the slides for a moment. Give me one sec. Okay, hopefully you can see the slides again. Is that right?
Yes.
Okay, very good. So before we begin, because this is going to be, we have a very limited amount of time, I want to start by mentioning two things. The first is getting into the details of Josephson junction physics, or the physics of how superconductors work itself, can be quite an overwhelming bit of material. And I've put together these two references that can help you dive deep if you're very interested in this work. The first one is a recent review on superconducting qubits, and this is came out in 2019 first, but has been reviewed as late as 2021. The second is a bit of an older paper, but it does have a very pedagogical presentation. It's from 2004, and I think it's actually interesting for you to see how the language in the field and how qubits themselves have changed between 2004 and 2021. So I recommend looking through this as well if you're getting started. So with these references in hand, let's go quickly through how we would make qubits out of superconductors. And I think as you talk about making qubits out of any material, I think as you go through this course, you've probably seen the DiVincenzo criteria mentioned over and over again. And that's a very helpful framework to think about how we make qubits. Incidentally, this morning, I looked up how many times the DiVincenzo criteria paper has been cited. It's cited well over 3,200 times. And it's one of the most helpful documents that has shaped the field in the sense of, even if you ask DiVincenzo, he'll tell you these criteria are exactly the ones that you would teach the kindergarten children about computers, quantum or otherwise. And because these criteria are so helpful to think through how we make quantum computers, they've really helped push the field forward. So let's go through them. I'll focus on a couple of them first, and then we'll go through the rest very quickly and pass it on to Sabrina and Daniel. So step one is that the first of the DiVincenzo criteria says we need to have a well-defined scalable qubit. So let's break this down into two pieces. I first want to tell you about what this well-defined qubit means, and then we'll talk about the scalable aspect of it. So first of all, to define a qubit, you might have, for example, heard about spin qubits in your past lectures. The spin of an electron, for example, provides a very nice two-level system that you can use as your qubit, where you define 0 as spin up and down as spin down, for example, down as the one state, for example. So you have a very well-defined set of states. In this situation, we're going to be engineering our qubits by making quantum circuits. And what do I mean by this? If you go back to sort of what you know about a harmonic oscillator, the energy levels of a harmonic oscillator formed, for example, from an inductor and a capacitor. You might be thinking, if you have a mechanical engineering background, for example, about a spring mass system. At the end of the day, the energy levels are coming from a parabolic potential, and they're equally spaced. The spacing of these levels is defined as the sort of resonance frequency of that harmonic oscillator. And in order to engineer something very similar to this using superconducting circuits, we replace that inductor by something that looks like an inductor, which is that Josephson junction that I showed you a moment ago. And the net effect of that is, instead of a parabolic potential, we end up having a cosine potential. And that small perturbation from being more like a cosine instead of a parabolic potential means that these energy levels are now spaced out. When they are spaced out, what that means is the space between your 0 and 1 levels, and the space between your 1 and 2 levels, and the space between your 2 and 3 levels are all well defined. And so you can identify 2 of these levels as your qubit, and that frequency between 2 of these levels is different from the others. And so you can specifically address that frequency. In a harmonic oscillator, you couldn't do this addressing, right? Because this frequency is not unique. And so what you have here is a change to something that looks like a harmonic oscillator with a slight change here with the Josephson junction. From a more fundamental perspective, what you're doing is taking a harmonic oscillator and adding a bit of nonlinearity to it through this Josephson junction. And that nonlinearity is what takes you away from this parabolic potential and into this cosine potential. Now, this is all fine and good, but if you really look at the papers, for example, these are pictures from our Beyond Classical experiment, you'll see pictures that look like this. So here's for example, the device. What it really looks like is this is the chip is flipped onto another package. And so you have the qubits on one chip, you have the wires that connect to the outside world on another, and the qubit chip is flipped onto the other one. And together, these two form the quantum computer that is then packaged to the outside world. The individual components in the paper are drawn like this, and that's for a reason. And that's because the structure of the system itself, if you zoom in on the devices, looks like this. Now, this is the part where I'm going to tell you a little bit about the structure of these qubits themselves. They're called transmons based on the set of parameters you choose for the inductor and the capacitor. But fundamentally, by replacing this one Josephson junction instead by two Josephson junctions, you're allowed to insert a magnetic field into this loop, which will then, because it's a flux threading this loop, which is made out of superconductors, allows you to change the effective inductance. Remember, this loop is trying to be sort of similar to the inductance that you have in a harmonic oscillator. And that gives you a frequency tunable qubit. The circuit representation of this on the real system looks like this, where you have control knobs that come next to the qubit, and you have the qubit structure itself with the capacitance pad to ground, as well as the Josephson junctions themselves. So hopefully this gives you a sense of the physical system that is used to make these things. But at the end of the day, the well-defined qubit comes from changing slightly away from a harmonic oscillator by using a nonlinear inductor, and that comes from using Josephson junctions. And then the scalable part of it comes from, one, coupling each of these to one another capacitively or using tunable couplers, and two, from being able to then drive these qubits themselves by control knobs. So this structure hopefully gives you a sense of how we satisfy the first of the DiVincenzo criteria. So in the interest of time, I'm going to move very quickly through the rest of these. The second of the DiVincenzo criteria is the ability to initialize the qubits. And as I mentioned before, the systems themselves are made out of superconductors. And one simple way to initialize the ground state of that cosine potential that I mentioned to you is to simply wait as long as a time scale that we call T1. And that has the effect of bringing all your excitations to the ground state. But in order to make that happen quicker, I'll point you to just a paper here that came out from the team. We've also come up with very clever pulse sequences that you can apply to the qubit that in the end, without that reset pulse sequence versus with that reset pulse sequence, you can see on a grid of several qubits, the population of not just the 0 and 1 state, but the 2 state, which also tends to be a challenging problem in our field, can be brought down to very close to 0%. And the point here is not to just bring everything down to the 0 state, but really to have a well-defined initialization. So what we're doing here is bringing all the excitations down to the ground state. The third, fourth, and fifth of the DiVincenzo criteria I'll go through very quickly here as well and pass it to Sabrina and Daniel. The third one is the question of having long relevant decoherence times. Again, this is one of these simple sounding statements, but really what we're talking about here is you might have heard about systems that have decoherence times of order 1 second, 10 seconds, 100 microseconds. What we really care about is the relevant decoherence time, and that means your coherence times relative to your gate times, how quickly you can apply operations to your quantum computers. And so in our systems, we're dealing with gate times of order 10 nanoseconds and coherence times of order 10 to 100 microseconds. So about 1,000 times larger than the gate times. And so that gives you an idea of the kind of physical system and the ability that it has. So the fourth and fifth ones are related to being able to do a universal set of gates and to be able to read out the quantum computer. So to talk through these, I'll ask Sabrina and Daniel to take over. So maybe for the next section, we'll have Sabrina take over to tell us about gates and how we characterize them in the system.
Great, thanks, Abe.
Yeah, no problem. Do you want me to switch slides for you, or would you like to present from your screen?
Yes, please. If you can go ahead and do the slides, that'd be great.
Yeah, no problem. Okay.
Awesome. So yeah, this section is going to be a little bit about system control. So we've already gotten a flavor of this from Abe's introduction, but the superconducting processor that Abe just went through, those circuit components, is really one part of a much, much larger system. that is required to operate a superconducting qubit processor. So there's the fabrication of the actual device. There's the packaging. So, there's those wires that are printed onto the circuit themselves, but then we need to be able to expose those to the control electronics to control them. So we have microwave packaging that does all sorts of things, isolation being one of them, which gets loaded into a dilution refrigerator. And there is a ton of work that goes into the cryogenic hardware that is inside of that system to further isolate our qubits from external noise and radiation and things like that. And then there's also on top of that, the control electronics and room temperature wiring that goes to this cryogenic hardware. And really, for superconducting qubits, we think of continuous research and development being required in every single one of these areas to continuously improve system performance and scalability. So in particular, we can fabricate more and more qubits, but if they don't fit into a dilution refrigerator and we can't cool them down with all the control lines, it's not particularly useful. So, there's research that goes into, for example, miniaturizing things, making electronics be able to work at cryogenic temperatures, being able to, instead of have individual cables, make ribbons, all these sorts of things that go into engineering kind of this full stack superconducting system. If you can go to the next slide. Okay, so now we have all this hardware, we have this full system. Am I going to be able to run Shor's algorithm? Are we quantum computing yet? And the answer is no. So again, in that DiVincenzo criteria, you need a universal gate set. And so our gate-based quantum computer needs two things, gates and measurement, which sounds fairly obvious. But the thing that we need for gates is instructions. So to be able to perform a gate, the electronics need some sort of instructions for how to produce certain microwave and DC pulses that are equivalent to, say, a pi pulse or a Hadamard gate or an X gate or a Y gate or things like that. And also we need to be able to measure the return signals from the device itself. So for example, if I'm sitting at my laptop and I say, okay, I want to initialize a qubit in the ground state, apply some X gate and measure, those instructions need to go to some host computer, which then goes to the electronics, which creates some microwave signal, which goes down into the cryostat, into the device itself. So if we go to the next slide. Determining that correct set of instructions is something that we refer to as calibration or device calibration or gate calibration, but just calibration in general. So what happens is we start from knowing very little about the characteristics of each qubit and resonator specifically, aside from what was kind of designed and some of the things that you might be able to determine from room temperature measurements. And basically what the process of calibration is a series of different experiments where you start to characterize more parts of the system and calibrate parameters of each qubit. And it goes through a bootstrapping process, and I'll go through that in a second, until we have calibrated gates. So if you look at the figure on the right, for example, if you're thinking about a single qubit, a single transmon, you have a single qubit that is coupled to a readout resonator. So first you need to figure out, okay, how do I read out the state of this qubit? I might perform something like resonator spectroscopy to find out where the center frequency of that resonator is, and also what kind of power I need to drive my microwave tones at to be able to address the qubit without saturating anything. And then, okay, so once I have that information, I'm able to now measure the state of the qubit. So I can perform something like qubit spectroscopy, for example, where now I can figure out, okay, what is the qubit frequency? And I can also estimate, for example, what is an amplitude that I might need to be able to do a pi rotation. And that just goes on and on. As for each step, you start to learn a little bit more information about the qubit itself, and then you can start to calibrate gates. So you can do gate optimization, readout optimization, and eventually get to benchmarking the gates that you have. And one thing that I'd like to note is that for these tunable transmons, they're about on order 100 parameters per qubit that we need to be calibrating and characterizing. Sorry,
Sabrina, just out of curiosity, and
yeah.
Is it like a once in a lifetime for each chip, or do you need to recalibrate? Does it degrade over time, or like how often do you need to recalibrate stuff?
That's a really, really great question. So in a perfect world, right, it is once you bring up the device, you find out a lot of information about it, and then it stays that way. The reality is that that's not true. There are, some more classical things that you could consider. We use classical electronics, and that has amplifiers in them, and amplifiers can drift if there's room temperature drifts, for example. And so you can imagine that the DC pulses or the DC biases that are going down to the qubit are changing as a function of time, which means that you will need to recalibrate these parameters to compensate for that sort of drift. Another thing that isn't quite classical is our superconducting qubits are fabricated. They're on, on these silicon wafers. And so, for example, there are defects that these qubits can actually couple to, which we often will just call two-level systems as a blanket term. And these two-level systems can also fluctuate with time, which means that the qubit might have been isolated and not coupled to anything for, the whole day that you were calibrating the device. And the next day decides there's a two-level system that rolls into town, and you have to now deal with the emergence of that. And I'll actually talk a little bit about how we deal with that. Awesome. So yeah, this calibration process, again, like I said, is a bootstrapping process. You learn more about it as you go. And you can imagine at any given point, if something is broken, you can get a no or no go criteria, or things that tell you, hey, it's just not going to work. Go back to the drawing board, design a new qubit, things like that. All right, next slide. Okay, so this is going to get into specifically for tunable transmons. Everything that I kind of said before about calibration is largely hardware agnostic. Every qubit platform needs to be calibrated, but this frequency optimization step is really kind of unique to the tunable transmons that we use. So again, like Abe mentioned, you can apply some bias, and that sends some flux through a squid loop, which changes the effective inductance of the circuit that you have, which means that our transmons basically have tunable frequencies, which means that omega 01 that you saw is going to change based on how much flux is going through the squid. And this is by design. Frequency tunable transmons are great because they provide a really wide range of possibilities when you configure the system as a whole. So there's one problem, which is being able to calibrate single and 2 qubit gates. It's another problem being able to execute all of those gates at the system scale when you have problems like, for example, crosstalk, or if you have uncontrolled couplings between like next nearest neighbors, for example, or if you introduce this like two-level system component that might be changing as a function of time. And so one of the things that we have to do is take all of these things into consideration and optimize the processor, optimize at each qubit level, at each gate level, what frequency we want these things to be at. And this optimization is really, it's high dimensional. It really exceeds the Hilbert space dimension of the processor. And it's a complex problem that the Google group is working very hard on, finding out ways to do this in an efficient manner through optimization, through introducing as much known model parameters about the device that we have. So in this particular figure, bear with me for a second, on the far left, you're starting with, let's say I have a grid of qubits where each square is a single qubit and the color map is its frequency. Let's say we start with everything at the same frequency. Now we're going to control for noise, for example. We want these things to be at a point where they are insensitive to, for example, flux noise. That changes what that map looks like. Okay, so now let's say we add in some pulse distortions. What does that look like? Let's say we add in this coupling between nearest neighbors. What if we add coupling between next nearest neighbors? So you can see that as you start to add the complexities of operating something at the system scale, you end up with a much more diverse kind of landscape of what is the optimal frequency that you might be using to operate the system as a whole. Okay, and if we can go to the next slide. And this opens the question for, qubit processors are only getting larger and larger. For example, the Google Sycamore processor has 54 qubits and 88 tunable couplers between those qubits, and we are continuing to scale to much larger devices. And on the right, what I have there is a directed acyclic graph, which kind of shows you like calibration sequence for just 2 qubits. So calibrating 2 single qubits and then a 2 qubit gate that interacts them, where every single one of those circuits, every single one of those circles is a different experiment, kind of like in that flow diagram that I was showing you before. So this graph has a ton of information on it. In this graph really has decades of research worldwide of like how we've come to learn to calibrate superconducting qubits. But this is only for 2 qubits. And again, for like the Sycamore device, which has 54 qubits and 88 couplers, there are thousands of these circles. So it's a really, really important kind of research goal to be able to automate these systems, to be able to calibrate quickly in a way that, like Clarice mentioned earlier, you might have to do this again because things drift, and you have to do it on a time scale before things drift. So automation and scaling of these things is an active area of research within our group. And with that, I think I will pass it off to Daniel.
Okay, am I hearable?
You are audible.
Yes.
Thank you. Abe, can you exit presentation mode and then go back in? I tweaked one of the slides.
You got it.
All right. My name is Daniel Sank, and I've been at Google since 2014, and I work primarily on Qubit Readout. So my goal for the next few minutes is to explain the very basics of how we do readout of the qubits that Abe and Sabrina have talked about so far. Okay, so first I want to explain why it's difficult to read out a transmon qubit. The circuit diagram you see on the left has a capacitor and a Josephson junction in parallel. That's a transmon qubit. Now, as a quantum mechanical object, this thing has a cosine-shaped potential energy, as Abe showed you earlier. And if you focus on one of the wells in that cosine, it looks kind of like a parabola, but it's got some funny curvature to it, as Abe explained. And as you already know or will learn, when you solve for the quantum wave functions in a funny shaped potential, you get things that look like what's shown here. So the blue line, which looks kind of like a Gaussian function, is the ground state. The red wiggle is the first excited state, and the green wiggle is the second excited state. Those are more or less probability distributions of what the qubit is doing. And it's a funny idea, because if you look at what the x-axis of this plot is, it's magnetic flux. So what these things are telling you is that if the qubit's in its quantum ground state, and it's in that Gaussian distribution, then if you were to measure the amount of magnetic flux in that Josephson junction, you would get a random number, and it would be drawn from the probability distribution represented by that blue curve, and similarly for the red and green curves. Now, the thing that makes the transmon so hard to measure is that if you look at all of those distributions, they all have 0 for their average. So whether the qubit's in the ground state, the first excited state, or the second excited state, you can't tell the difference by measuring the magnetic field. What you would have to do is measure it many, many times over and over to build up a probability distribution, and then you could figure it out. But in quantum mechanics, when you measure something, you collapse the wave function, kind of get rid of all the quantum information. So you only get to measure once, and you're most likely to just get, you can't tell the difference because they all have the same mean. The same story goes for the charge on the capacitor. So you're really in a hard spot. Now, another thing you might imagine doing is saying, okay, well, if the qubit's in the first excited state, then it has a different amount of energy than if it's in the ground state. So maybe we can measure the energy. But that's hard because the resonance frequency of these qubits is in the range of gigahertz. And the energy of one quantum of energy, the energy of one quantum at that frequency, which is the frequency times Planck's constant, is about 0.2 microelectron-volts. And that's really, really small. There aren't any conventional ways of measuring energies at that small of a level. Like optical photon counters work, optical photons are many thousands of times higher in energy, and they don't work at this level. So you can't measure charge, you can't measure flux, you can't measure energy. So what do you measure? How do you tell which state this thing is in? So the key really comes down to the fact that, as Abe explained before, this thing is nonlinear. So its resonance frequency depends on how much energy is in it. And we're going to exploit that to do readout. Abe, could you go to the next slide, please? Okay, so now let's, just to give another angle on this whole thing, let's think about what happens as the transmon evolves in time. But let's start with a classical inductor capacitor oscillator. If I start with just a little bit of charge on the capacitor and I let it go, what's going to happen is the charge will leave the capacitor and flow through the inductor to get to the other side. So you'll start with a bunch of charge, but then as time goes on, the charge will go to 0, but the flux in the inductor will go up. So that's going from, in that top graph, that's going from the top of the circle to the right side. And then the inductor will start to discharge and push charge onto the other side of the capacitor, and so the charge will go negative, and so forth and so on. In classical physics, with a harmonic oscillator, if you use this this sort of phase space picture, you go around in circles. Now, that's a thing that you can easily measure in any lab with a regular LC oscillator. You can just use an oscilloscope, and usually you measure the voltage, and you can see that the charge or the voltage is oscillating in time. Now, the difference is that in quantum mechanics, states of definite energy don't have a well-defined phase in this plane, in this two-dimensional plane picture that we're using here. So in fact, that ground state that I mentioned in the previous slide, that Gaussian distribution in flux, it's actually a Gaussian distribution in both flux and charge. And if you look at it in the two-dimensional picture that we're showing here, it just looks like a blob centered at the origin. So if you slice it along flux or you slice it along charge, you'll get a Gaussian distribution, but it's just this isometric Gaussian ball. Similarly, for the first excited state, you get something that looks kind of like a ring. And the point that I'm trying to make here is that neither of these evolve in time. If you put the qubit in the first excited state, it is a superposition of all possible phases around that circle, and it's not oscillating. There's nothing you can measure there either. So that's just to give you another kind of feeling for the fact that it's hard to measure these qubits because, as I mentioned before, there's no charge signal, there's no flux signal, nothing is evolving in time. The energy scales are very small. But I did say that the frequencies are different. So let's dig into that. Abe, next slide, please. Okay. The way that we actually do measure transmon qubits is called dispersive readout. And this slide gives an intentionally very oversimplified idea of how that works, but it does get the main idea across. Take a look at the circuit diagram on the left of the slide. We have the transmon qubit, which can be in either the 0 or the 1 state indicated in blue or red. And we connect it, let's say through a capacitor, to a waveguide or a transmission line. We send a voltage pulse, V in, into that transmission line, and it reflects off of the capacitor and qubit. And because the frequency of the qubit is different in the 0 and 1 state, the phase of that reflected signal depends on which state the qubit was in. So what we do is we shoot in that pulse, and then we capture the reflected pulse and look at its phase. And that's how we tell which state the qubit was in. Now, in some sense, the trick here is that we're kind of supplying the energy for the measurement from the outside. So we put enough energy in this pulse that it's something we can actually measure. Because remember, the qubit doesn't have enough energy inside to tell us which state it's in, at least not in a straightforward way. So we put the energy in ourselves and we let the qubit adjust the phase of the energy in that pulse, and then we measure that phase. So that's the trick. All right, Abe, next slide, please. Okay, so now let's just take a look at some of the details. And mainly the reason I wanted to show you this is that if you look at other talks or papers, you'll see a lot of plots that look like what I'm going to show you here. And I wanted to give you this sort of mental vocabulary to digest them. So let's think about what happens if you shoot a voltage wave in and you just have a capacitor to ground. There's no qubit, no oscillator, anything like that. Well, there's no resistance or anything to absorb the energy here. So all the energy comes back out. And there's no phase dependence. Let's say this capacitance is really tiny, so it's basically just an open circuit. So as a function of frequency of that pulse going in from the left, the amplitude and phase are both constant. That's what's shown on the right. Very simple plots, horizontal lines. All right, next slide, please. Now, what happens if we put a resonator instead of just an open circuit. Now there's a special frequency, namely the resonance frequency of the resonator itself. And what happens is there's still nothing to absorb any energy. So all the energy comes back. So the amplitude is still a constant function of frequency, but the phase is not. So now what happens is, as we change the frequency of the input pulse, you'll see that the phase of the reflected pulse goes from 2 pi down to 0 as you sweep through the resonance. This is just something, you can work this out based on Kirchhoff's laws and basic circuit theory. Yeah, this is the basic principle of the measurement. And then Abe, next slide. Another useful way to plot this is on a two-dimensional axis. So here, what I'm plotting is the amplitude and phase of the reflected signal on a two-dimensional grid. So amplitude is distance from the origin and phase is the angle. And what happens is that if you're below resonance, so you're at low frequency, then you start on the left upper part of that circle. And as you sweep the frequency of the drive pulse, you wind up making a circle in this plane where the resonance is where the circle hits the x-axis on the right side. Now, what happens is that this circle, the resonance point of the circle depends on what the resonance frequency of that resonator is. So Abe, next slide. Okay, so if you have a qubit where the resonance frequency depends on the state, now what happens is that you hit that resonance at different frequencies. And so in the upper right plot, you'll see that there's two phase curves, the blue one for the qubit in the ground state and the red one for the qubit in the excited state. And they're separated by some distance on the frequency axis. That separation is called 2 times chi. That's just some jargon that you might see in papers. It's called the dispersive shift. But the point is that they're separated. And so if you drive right in the center there, so there's that label that says probe here for good contrast. What that means is we shoot that voltage input pulse at that frequency so that the phase of the 0 and the 1 state of the qubit are as far apart as possible. So you just look for the point where the contrast is the biggest, you send in your pulse there, and depending on which phase you get, you know which state the qubit was in. Now, the data that we usually collect is shown in the bottom right plot. So here I'm showing that two-dimensional plane again with amplitude and phase of the reflected signal. And you can see, oh, this is real experimental data, by the way. You can see that the blue points, which are for the qubit in the ground state, is over on the left, and the red points for the qubit in the excited state are over on the right. They both have the same magnitude, but they have different phases for the reasons that we've been explaining. Now, you can also see that there's a bunch of scatter in those points, and that comes from the fact that there's noise in the system, and it adds some randomness to the points you get out. And the whole game of doing this readout is to, you need to use enough power and enough time to get those clouds of points far enough away from each other that you can distinguish them despite the noise. But you also can't put too much power into the drive pulse, into the readout pulse, because if you do, it messes up the qubit state. So there's a delicate balance. Next slide, Abe. Okay, so why is this hard? So I'm just going to give a couple of comments about what makes this difficult. First of all, this, as I just mentioned, you can't use too strong of a signal for that readout pulse, because if you do, it screws up the qubit. The signal pulse power that we use is minus 120 dBm. For those of you who are unfamiliar with this scale, what you do is chop off the last digit, and what you have left is the power of 10 for the power. So minus 120, chop off the 0, it's minus 12. So this is 10 to the minus 12, and the M means milliwatts. So we're doing this readout with 10 to the minus 12 milliwatts of power. It's extremely weak power. And in fact, it's so weak that in order to amplify it enough to actually detect it with lab equipment, you have to amplify it by a lot. In fact, you have to amplify it by a factor of about 10 billion. So that's one of the first things that's hard about this, is that you have to use very weak signals. You have to amplify it by this huge amount. And those amplifiers have to live inside of a cryostat. And amplifiers dissipate heat. So finding amplifiers that have enough amplification and low enough noise without heating up the cryostat is very hard. And in fact, we make some of our own amplifiers, which is one of the really interesting projects on our team. There's some notes here. I assume the slides will be shared with you later, so you can take a look at some of the numbers, but there are some numbers here to illustrate kind of why getting this all to work is a little bit difficult, but I'm not going to explain it because we're short on time. Next slide, Abe. Actually, I think that might be the last one. Oh, yeah. And I just wanted to show that, you know, all those amplifiers and everything have to go into that space that Abe showed you earlier inside the cryostat. So here's a zoom in. You can see the size of the human hand. So the space isn't really all that big. We measure 5 or 6 qubits per sort of readout, per set of readout amplifiers. So we wind up needing a lot of amplifiers in a small space. Those all take up a lot of room. The wires themselves take up room. And so one of the interesting engineering projects on our team that affects readout very strongly, and other things, is finding ways to miniaturize all of this hardware while maintaining the performance. And there's some really interesting tricks using superconducting circuits and other kind of exciting new research that goes into that. Okie dokie. That's it. I'm done.
Okay, thank you, Daniel. That was very insightful. And I think, Clarice, at this point, we want to open up the floor for questions or anything that students might have to ask about. But I'll just say, I hope all of this has given you a sense of both the profound challenges that we have confronting us to make these quantum computers useful, as well as the sort of potential of these quantum computers. At the end of the day, as we think about scaling these qubits, when you see some announcement about a roadmap or an improvement in quantum computers, really contextualize it from the perspective of what you saw, which is in the DiVincenzo criteria, these changes are trying to make this part of it a little better. And hopefully you can compare the trade-offs with other quantum systems as well. Okay, so I'll pause it here and leave for questions.
Would each of you maybe give like a 2-minute introduction on how you became a quantum engineer in the industry?
Sure.
Abe, you go first.
Abe, you go first, yes.
This is a trap that you're making me go first. I did undergrad in EE, and I did my graduate studies in quantum computing, but on the experiment side, focusing on using electron spins of electrons floating on superfluid helium. When I started graduate school, the path and the questions most were asking were along the lines of, how do I get a good qubit with a good T1 and T2? So really confronting that first of DiVincenzo's criteria. It's really interesting to see some 10 years later that the field is no longer thinking about that problem, but is now confronting questions like you saw that Sabrina and Daniel touched on. So it's a very interesting place to be, and that's why I chose also to stay in the field and continue being part of it. Yeah. I will tag team Sabrina into this one next.
Sure. Right. So I did mention I am a UCLA alumni. So I did my bachelor's at UCLA in astrophysics, and actually I took a slightly atypical route to quantum computing. I went straight to industry. I like skipped the academia part. And I actually started not in superconducting qubits, but in silicon quantum dots. This is another kind of fabrication-based circuit kind of thing. Very, very different problems from superconducting qubits, but very interesting nonetheless. And yeah, I also was at a couple different startups that were doing quantum computing for a little bit. One of them was doing neutral atom-based quantum computing. So again, a different architecture, not superconducting qubits, but I am back and doing superconducting qubits. And it is an interesting technology when it comes to scale. And there are lots of problems, I think, that all of the different hardware components need to tackle. There is complexity. It's just a matter of where you push it. Is it in control? Is it in fabrication? Is it in your experimental setup? There's a lot of, there's a lot of physics research, but I think also in addition to that, there's a lot of engineering that needs to happen along the way.
Okay. Well, when I was a kid, I wanted to build cybernetic body parts for disabled people. Then I got to college and worked in a biophysics lab, and I didn't love it, so I was kind of looking around. And I thought quantum mechanics was totally wrong. It made no sense to me at all that quantum mechanics could be correct. And then a professor of mine, who's actually now on sabbatical in our group, which is super awesome, said that quantum mechanics works for everything, not just microscopic stuff. And then I said, okay, if that's true, then I believe it. So I went to grad school at UCSB with John Martinez to see for myself, and it turned out it works. So I was sold, and I'm still in the field. Honestly, I think the reason I'm still in this field is that it's so diverse technologically and intellectually that you just never, ever, ever get bored of it. Like in my job so far, I've gotten to do electronics, software theory, cryogenics, microfabrication. Like you can always find a project to learn something new. And for me, that's the best part.
What are your questions, students? Just unmute yourselves and ask away.
And I'll just say very quickly while people are typing in the chat, I think Sabrina might have to drop a little early. We'll miss you, but thank you for making the time to join us here. And yeah, let's see what the questions are.
Thank you so much. So you have those wonderful quantum engineers, quantum experts. What do you all want to learn from them? What are you curious about?
I saw you guys are using XMO instead of floating transmon. Is there like a particular reason for that?
Using XMON instead of what? Say again?
Instead of like a floating transmon structure.
Oh, those are huge and very hard to couple to each other. I don't know if that answers the question.
Yes, thank you.
They're big. They're like the size of a cell phone. They're way too big to make something integrated with many, many qubits.
Are there like plans to make the usual amplifiers go cryogenic or something?
Did Sabrina just drop off?
Yeah, I think Sabrina might have just left us.
Okay. When you say the usual amplifiers, so the amplifiers are mostly for readout, and we have already two different kinds of amplifiers inside the cryostat. There's parametric amplifiers, which are special because they have extremely low noise, and we actually make those ourselves. So those are microfabricated, and they're in the fridge with everything else. Then the next stage amplifier is something that we buy. It's an amplifier based on what's called a high electron mobility transistor. And right now, I would say those are the biggest problem. They dissipate a lot of heat, and they're pretty big. So making those smaller and dissipating less heat is actually one of our main areas of research right now.
Well, thank you all again for answering our questions and giving us this wonderful and insightful talk. You've given us a lot to think about, and we really appreciate you being here. The time is 1:01 p.m. I know our students, we're in week 8, so it's the countdown to finals. So I think we're going to stop here and dismiss the class. Thank you all for joining us.